By the summer of 1942, the United States Navy had one fleet carrier left in the Pacific that wasn't damaged, sunk, or under repair. 1. Japan had just proven, at Coral Sea and Midway, that carrier battles could erase a nation's naval air power in a single afternoon. A ship that took 3 years to build could be gone in 20 minutes. The Navy did not respond with a better carrier. It responded with a faster one. Not faster in the water, faster off the ways. In Newport News, Virginia, and Camden, New Jersey, shipyards abandoned the old method. One carrier, one custom design, one slow and painstaking build, and committed instead to something almost unheard of in warship construction. A single standardized blueprint, repeated hull after hull, on a production line built for war. 24 of these ships would be launched before Japan surrendered, most of them in under 2 years each. This was not a bet placed after a victory. It was placed in 1940, before Pearl Harbor, before anyone knew if a single one of these ships would ever see combat. The wager was simple and brutal. Build carriers faster than an enemy could sink them. By 1944, off the Philippines, the answer to that wager would arrive in the form of a fleet so large the Imperial Japanese Navy could no longer field enough aircraft to challenge it. This is the story of how a shipyard schedule decided the Pacific War. In 1938, an American aircraft carrier was not a product. It was a project. Each ship began as its own set of drawings, argued over for months inside the Bureau of Construction and Repair, then handed to a single yard that built it as a one-off. Its own hull form, its own machinery arrangement, its own internal layout, refined and re-argued at every stage. The Yorktown-class carriers, the best ships the Navy had, were built this way. 3 ships, 3 years apart, each one a fresh negotiation between admirals who wanted more armor, aviators who wanted a bigger air group, and engineers who had to make the numbers fit inside a hull that could still make 30 knots. A shipyard floor in this era looked like a cathedral under construction. Riveters worked a single keel for months before the first frame ever took shape. Plans changed mid-build. Machinery came from suppliers who cut parts to fit one ship, and one ship only. A boiler built for USS Yorktown could not simply be dropped into USS Enterprise. Every carrier was, in effect, a prototype that happened to also be a warship. This was not incompetence. It was the accepted logic of naval construction going back to the age of sail. A warship was too complex, too consequential, to be treated like a factory product. Custom-built meant carefully built. Slow meant right. No navy on Earth built capital ships any other way. The Japanese did not. The British did not. The idea of a fleet carrier as a repeatable mass-produced object did not exist anywhere in 1938 because no one had yet needed to replace a fleet carrier faster than an enemy could sink it. That need did not exist yet. It was coming, and when it arrived, it would not announce itself in a design meeting. It would announce itself in the water, off a Pacific atoll, in the space of a few minutes, when the United States Navy discovered exactly how fast a carrier could disappear, and how long it took, under the old system, to build another one. Before the war forced the Navy's hand, the argument was already underway inside the Bureau of Ships, and it was not an argument about whether carriers mattered. It was an argument about what a carrier was for. One faction, rooted in the design philosophy that had produced the Yorktown class, argued for continued refinement, more armor around the flight deck and magazines, larger air groups, better protection against the plunging shell fire and torpedo hits that had haunted naval planners since the battleship era. To this faction, a carrier's value lay in its individual survivability and striking power. Build the best possible ship, even if it took years, because a single superior carrier could be worth 2 average ones in a fleet engagement. A second faction, smaller but growing louder as war in Europe and tension in the Pacific escalated through 1939 and 1940, argued a different case entirely, that the coming war would not be won by any single ship, no matter how well built, but by aggregate capacity. How many hulls could be in the water, launching aircraft, at any given moment? To this faction, a carrier lost was not primarily a tactical setback. It was a production problem, and production problems were solved not by better design, but by repeatable design. The tension between these two positions was not abstract. It played out in specific trade-offs that naval architects had to resolve on paper, hull by hull. A thicker armor belt meant more steel, more welding hours, more weeks added to a build schedule already measured in years. A larger air group meant a longer flight deck, which meant reworking the ship's structural framing, which meant every yard building the design had to relearn the ship from the keel up. Every improvement, however sound in isolation, threatened the one variable the second faction cared about most: how fast a yard could go from keel laying to commissioning. This was the quiet, unglamorous fight that would determine how America built its Pacific carrier fleet. Not a battle, not a headline, but a series of memos and design reviews inside the Bureau of Ships, where engineers had to decide whether the next generation of carriers would be optimized like the Yorktowns had been, or standardized like nothing the Navy had ever built before. The decision, when it came, was not unanimous, and it was not obvious. Standardization meant accepting a design that was very good, rather than continuing to chase one that might eventually be the best. It meant telling admirals who wanted more armor, more range, more everything, that the ship they would get was the ship that could be repeated. Because in the war that was coming, the Navy would not need one perfect carrier. It would need dozens of good ones, arriving faster than the enemy could remove them from the board. That decision, quiet, procedural, made by men whose names would never appear on a hull plaque, is where the Essex-class began. The design that would become the Essex-class was authorized in 1939 and finalized through 1940, and it represented a deliberate compromise. A hull roughly 872 feet long, displacing around 27,000 tons standard, larger and better protected than the Yorktowns, but built around one governing principle that mattered more than any single technical feature. Every ship in the class would be built from the same set of drawings, with only minor yard-specific variations, and no fundamental redesign between all hulls. This was the break from tradition. Not the armor, not the air group of roughly 90 aircraft, not the deck-edge elevator, borrowed from the earlier USS Wasp and refined for this class. The break was the decision that hull number 2 would not be an improved version of hull number 1. It would be the same ship, built again, by a workforce that had already learned every rivet pattern and cable run the first time through. To understand how radical this was, consider what it replaced. Under the old system, a shipyard building, a Yorktown-class carrier employed skilled tradesmen who solved problems as they arose, because every problem was, to some degree, new. Under the standardized system, a shipyard building an Essex-class carrier employed the same skilled tradesmen, but the problems had already been solved once on the first hull, and the solution was now a fixed procedure that could be taught, repeated, and sped up with each repetition. The Bureau of Ships formalized this by issuing a single master set of construction plans to every yard building the class, rather than allowing each yard to develop its own approach to the same general design. Deviations required sign-off. This sounds bureaucratic, and it was. But the bureaucracy existed for a specific purpose: to guarantee that a boiler built in one city could be installed on a hull being framed in another, that a workforce trained on one carrier could be transferred to a second yard, and immediately understand the ship in front of them. The trade-off was real, and everyone involved understood it. A fully bespoke design might have squeezed out another 2 knots of speed, another few hundred tons of armor, a slightly more efficient hangar layout. The standardized Essex design left some of that performance on the table, deliberately, because the Bureau's calculation was not about what the best possible single carrier could do. It was about what 20 carriers, all seaworthy by 1944, could do that one exceptional carrier, still on the drafting table in 1944, could not. This was the moment the Navy stopped asking, "How do we build the best carrier we can?" It began asking, "How do we build enough carriers fast enough to survive losing some of them?" The keel of the lead ship, USS Essex, was laid down at Newport News Shipbuilding in April 1941, 8 months before Pearl Harbor forced the question from theory into emergency. The design existed. The commitment had existed. What did not yet exist was the industrial machine required to build 23 more ships just like it, at a pace no American shipyard had ever attempted for a vessel this large. That machine had to be built from nothing, inside two shipyards that had never before been asked to mass-produce a capital ship. Newport News Shipbuilding, on the James River in Virginia, had built battleships. It had built ocean liners. It had never built the same capital ship twice in a row without redesigning it. When USS Essex went down the ways in July 1942, the yard had already begun reorganizing itself around a question no American shipbuilder had needed to answer at this scale before. How do you build a 27,000-ton warship the way you build a rifle? As an assembly of standardized, interchangeable parts? The answer was prefabrication. Instead of building the ship as a single continuous structure from the keel up, section by section in sequence, Newport News and its sister yard, New York Shipbuilding Corporation, across the river from Philadelphia in Camden, New Jersey, began building major hull sections and equipment modules separately, in parallel, on different parts of the yard, then bringing them together at the building slip for final assembly. A boiler unit could be assembled and tested in a shop while the hull frame that would eventually hold it was still being erected 200 yards away. This required something the old bespoke system never had to solve: interchangeability of labor. A welder trained on the portside hangar deck framing of one Essex-class hull could be moved to the same task on a different hull, at a different stage of construction, and require no retraining, because the specification was identical. Newport News expanded its workforce dramatically through 1942 and 1943, drawing in thousands of workers with no prior shipbuilding experience, men and women who, under the old custom-build system, would have taken years to become useful on a capital ship project. Under the standardized system, they could be trained on a single repeatable task and made productive within months, because they were not learning to build a ship. They were learning to build one component of a ship over and over, to a fixed drawing. New York Shipbuilding and Camden ran a parallel transformation. The yard restructured its building ways to handle the Essex hull form, as a matter of routine rather than exception, and its subcontractor network, the companies supplying steel plate, turbines, fire control equipment, arresting gear, adjusted to producing to a single specification across multiple hulls, rather than custom-fitting parts for each ship individually. This mattered enormously, because a shipyard is only as fast as its slowest supplier. When every hull needed different turbines cut to different tolerances, the turbine manufacturer became the bottleneck. When every hull needed the same turbine, the manufacturer could tool up once and run the line. The results showed up first not in speed, but in predictability. USS Essex took approximately 20 months from keel laying to commissioning. Respectable, but not yet the pace the Navy needed. What changed over the next 2 years was not a single breakthrough, but the compounding effect of a workforce, a supply chain, and 2 shipyards all getting incrementally faster at building the identical ship, hull after hull, because they were no longer solving new problems. They were executing a known procedure with increasing efficiency. By late 1943, that incremental improvement had become something closer to an industrial rhythm, and 8,000 miles away, across the Pacific, an enemy shipbuilding industry that had never restructured itself this way was about to discover it could not keep pace with a machine it did not know had been built. Japan entered the war with one of the most experienced carrier forces on Earth. The pilots and crews who struck Pearl Harbor were among the best-trained naval aviators in the world. What Japan did not have, and would never build, was a shipyard system capable of replacing a lost fleet carrier on any timeline resembling America's. The numbers explain why. Japan commissioned only a small handful of new fleet carriers during the entire war: Taiho, Unryu, and a few others, built largely through the same custom, labor-intensive methods the United States had just abandoned. Each Japanese fleet carrier remained, in effect, its own project, built by a shipbuilding base that had neither the raw industrial capacity nor the institutional commitment to standardization that the Essex program represented. Japan's steel production, already a fraction of America's before the war, was further strained by competing demands from the Army, the merchant fleet, and a home island's economy stretched thin by 1943. The contrast sharpened with every carrier battle. At Coral Sea and Midway in 1942, Japan lost 4 fleet carriers, Soryu, Kaga, Akagi, and Hiryu, in a matter of months. These were not ships that could be replaced by keeping a shipyard running a little longer. They were ships that required years to build under Japan's construction methods, methods that had never been reorganized around the logic of repetition and interchangeable labor the way Newport News and New York shipbuilding had been reorganized in 1942 and 1943. The United States, meanwhile, was not just building Essex-class carriers. It was building them on a schedule that treated hull number 10 as easier than hull number 1. By the time Japan's shipyards attempted to accelerate their own carrier construction in 1943 and 1944, converting battleship hulls and merchant designs into makeshift carriers like Shinano and Unryu, the gap was no longer closable. Japan was solving, for the first time, the exact problem the U.S. Navy's Bureau of Ships had already solved 2 years earlier, and solving it under wartime shortages of steel, skilled labor, and time that America did not face in the same way. By the end of 1944, the United States had commissioned 17 Essex-class carriers, with more entering service in the months that followed. Japan, across the same period, had managed to add a handful of new fleet carriers to its order of battle, several of which were sunk before ever completing a full combat deployment, including Taiho, lost on her first major operation, and Shinano, sunk by an American submarine 10 days after commissioning, before she had embarked a single aircraft. This was the wager paying out in real time. The United States had not bet on building a carrier that could survive every battle. It had bet on building carriers faster than Japan could remove them from the war. And by late 1944, the math had become undeniable. America was not simply replacing its losses, it was outproducing Japan's ability to inflict them. What remained was to prove it in a fleet action large enough for the numbers to matter, and that proof was already steaming toward the Philippines. The numbers tell the story better than any single battle can. In 1942, the year the war truly began for American shipbuilding, the Navy commissioned 1 Essex-class carrier, Essex herself, in December. In 1943, that number jumped to 8. By 1944, Essex-class carriers were entering the fleet at a pace of roughly 1 every 5 to 6 weeks, a rate no capital ship class had ever achieved in American naval history. This was not a single dramatic leap. It was the visible result of everything built quietly in the 2 years before it. The trained workforce, the interchangeable parts, the supply chains tooled for repetition rather than customization, finally reaching full stride. Newport News and New York shipbuilding were joined by additional yards as the program expanded, each one absorbing the same standardized drawings, the same prefabrication methods, the same discipline that had turned carrier construction from a craft into a process. The compression and build time was staggering by pre-war standards. USS Essex had taken roughly 20 months from keel laying to commissioning. By 1944, later hulls in the class were being completed in closer to 14 to 16 months, a reduction achieved not by cutting corners, but by a workforce and supply chain that had simply gotten faster at executing a known procedure, hull after hull, the same way an assembly line gets faster the longer it runs. Behind these numbers stood a workforce that had grown to include tens of thousands of newly trained laborers, many with no prior shipbuilding background, now capable of framing a hangar deck or installing a boiler to exact specification because the specification never changed. Steel mills, turbine manufacturers, and equipment suppliers ran to a fixed schedule instead of a fluctuating one, because every hull ordered the same components in the same configuration. The entire American war production system, not just 2 shipyards, but the network of suppliers feeding them, had reorganized itself around the Essex class as a known, repeatable quantity. By the second half of 1944, the fleet math had become almost absurd in its imbalance. The U.S. Navy could field not 1 or 2 fleet carriers for a major operation, but a dozen or more in a single task force, the kind of concentrated air power that would have been unimaginable to planners arguing over armor thickness in 1939. Task Force 38, built around Essex-class carriers, alongside their Independence-class light carrier counterparts, could put more aircraft in the sky in a single strike than the entire Imperial Japanese carrier fleet had possessed at the height of its power in 1942. This was the payoff of the wager, arriving exactly as the Bureau of Ships had gambled it would, not as a single superior ship winning a single battle, but as an overwhelming self-reinforcing mass of carriers that Japan's shipbuilding industry had no realistic path to match. The fleet built to outbuild an enemy was about to meet that enemy in the two battles that would decide whether the wager had been worth making. On June 19, 1944, in the waters east of the Mariana Islands, the United States Navy fielded 15 fleet and light carriers as part of Task Force 58, a concentration of naval air power built almost entirely around the Essex-class and its light carrier counterparts. Japan, by contrast, could field 9 carriers, several of them undermanned and flying pilots, with a fraction of the training hours their American counterparts had logged, because Japan's carrier aviator training pipeline had never recovered from the losses at Midway 2 years earlier. The battle that followed became known among American aviators as the Marianas Turkey Shoot. Japanese carrier aircraft, launched in waves against the American fleet, were cut down in such lopsided numbers that some U.S. fighter pilots ran low on ammunition simply from the volume of targets. By the battle's end, Japan had lost roughly 600 aircraft and 3 carriers, including the newly commissioned Tai-Ho, sunk on her first major operation. The U.S. Navy lost approximately 120 aircraft, most of them not to enemy fire, but to fuel exhaustion during a long-range strike flown at the edge of the fleet's operational reach. The imbalance was not primarily a difference in pilot skill or aircraft design, though both factored in. It was a difference in what each Navy could afford to lose. The United States could send green pilots into the fight because it had the carrier deck space to keep training replacements at a pace the war demanded. Japan could not. 4 months later, in October 1944, the two fleets met again in the waters around Leyte Gulf, the largest naval battle of the Pacific War, and by some measures the largest in history. American carrier task forces, still built around Essex-class hulls entering service faster than the enemy could plan around them, provided the air cover and strike power that helped shatter what remained of Japan's carrier force. It was here, on October 25, that Japan first employed organized kamikaze attacks against American carriers, a tactic born directly from the recognition that Japan no longer had enough trained pilots or aircraft to win an air battle through conventional means. The escort carrier St. Lo was sunk by one of these attacks, a grim proof that Japan's naval air power, unable to match American numbers, had turned to a weapon that traded a pilot's life for a single hit. By the end of Leyte Gulf, Japan's carrier force existed in name more than function. Several of its remaining carriers had been reduced to decoys, sent north specifically to draw American attention away from the main battle, a tactic that succeeded tactically, but confirmed, strategically, that Japan no longer possessed a carrier fleet capable of contesting the Pacific on anything resembling equal terms. The wager placed in a shipyard drafting room in 1940 had been answered decisively in the waters off 2 island chains 4 years later. The question now was, what would happen to the design and the industrial machine behind it once the war that had justified its existence came to an end? When the war ended in August 1945, the United States had commissioned 24 Essex-class carriers, with a handful more completed just after the surrender. No other nation had ever built a fleet carrier class at this scale, and none would again. But the more consequential legacy was not the ships themselves, it was the method that had built them. The Essex program proved something the Bureau of Ships had only theorized in 1940, that a warship, even one as complex as a fleet carrier, could be treated as a repeatable industrial product without sacrificing the quality needed to win in combat. That lesson did not disappear when the shipyards stood down. It became doctrine. Post-war naval construction planning. From the Forrestal-class supercarriers of the 1950s through the Nimitz-class carriers that followed, inherited the same underlying philosophy: design once, refine incrementally, build to a standardized specification across multiple hulls rather than reinventing the ship each time. The Essex-class itself did not simply retire. Many hulls were modernized through the 1950s, under the SCB-27 and SCB-125 refit programs, angled flight decks, steam catapults, enclosed hurricane bows, and went on to serve in Korea and Vietnam, some remaining in active service into the 1970s. USS Lexington, one of the original wartime hulls, served as a training carrier into the 1990s. Nearly half a century after her keel was laid at a moment when nobody knew if the design would survive its first battle. The 2 yards that had carried the program are themselves part of this through line. Newport News Shipbuilding continued as the nation's primary builder of large carriers, eventually becoming part of Huntington Ingalls Industries, the company that builds every Nimitz and Ford-class carrier the U.S. Navy operates today. The standardized, repeatable design logic first proven on the Essex-class building ways remains, in essence, the same logic governing how a Ford-class carrier is constructed at that same yard on the James River more than 80 years later. New York Shipbuilding in Camden did not share in that long survival. The yard that had helped prove mass-produced carrier construction could work closed in 1967. Unable to compete in a post-war shipbuilding market that had consolidated around fewer, larger, better capitalized yards, a reminder that industrial capacity, once mobilized for a specific war, does not automatically translate into peacetime relevance. The historical verdict on the Essex program is, in the end, a narrow one, but a clear one. The Bureau of Ships did not build the most advanced carrier design theoretically possible in 1940. It built the design that could be repeated 24 times before an enemy's shipbuilding capacity could answer it, and in a war decided as much by production schedules as by tactics, that trade-off turned out to be the only one that mattered. The Essex-class was never the most advanced carrier design on paper. It was simply the one that could be built again and again, faster than an enemy could remove it from the war. That is the part of this story most documentaries leave out, that America did not win the Pacific Carrier War by building one unbeatable ship. It won by making the loss of any single ship survivable, because another one was already coming down the ways behind it. If you want to understand how the Second World War was actually won, not just in the cockpit or on the flight deck, but on the drafting table and the shipyard floor, that's exactly the kind of history this channel covers. Hit subscribe and turn on notifications so you don't miss the next one. We close, as we always do, on the ship itself. USS Lexington, one of the original wartime hulls, laid down before anyone knew if the gamble would pay off, sits today as a museum ship in Corpus Christi, Texas. Her flight deck open to visitors who walk the same planking where pilots once launched into the largest carrier battles in history. The bet placed in a shipyard drafting room in 1940 is still afloat.